Okay, we're going to talk about the material involved in section 3.3. I believe in your book they call it curve sketching, but it's really sort of a combination of a lot of the stuff we've been covering in the previous sections, and they sort of pull it all together. So let me try, and eventually I'm going to do a couple of problems, but I want to try and give you sort of a high-level explanation of what's going on. So I hope you understand why you do what you're doing. So initially, let me try and draw a diagram of what we're doing. So we're given some kind of a function, or it's really an equation. For instance, eventually I'm going to do two problems, and the first one is going to be f of x equals x cubed minus 2x squared minus 5x plus 6. And then there's going to be a second one. But this is a function, although it's also an equation. What we're going to do is we're going to go in and take a deep dive into this equation and try and learn all the stuff we can about this equation. Now what I want to do is I want to compare, there's two different kinds of problems we can have. And the first, sometimes you may be actually given a graph of a function or equation, and from that graph you can go in and determine all the important information. But then oftentimes you're just given the equation, and what I say is you have to do some math to figure out all the important stuff. Now the important stuff, just so you know, is going to be things like intercepts and domain and asymptotes and maximums or minimums or points of inflection or intervals where the graph increases or decreases, or where the graph is concave up or concave down. All the stuff we've been working on, and even more, is all the stuff we want to determine. And what I want to do is I want to first look at a couple of graphs, because I want you to be able to understand what we're going to do mathematically as it relates to a graph, because if you can visualize it, then a lot of times it makes it easier when you're doing the math part of it. Because oftentimes the last step in the math, they want you to sketch or sketch the graph. So ultimately, we're going to try and take this equation, and by all the stuff we've learned, try and make a sketch of the graph. So you need to understand the graph. So here's what I'm going to do. I'm going to give two examples, two different graphs, and let's just look at these graphs and determine the important information. So here's the first graph. I'm going to have to go back and forth. So here's a graph. These axes are just, each line is like 1, 2, 3, 4, and the same way on the y-axis. I didn't label these axes. I don't want it to be too messy. So here's this graph, and I'm going to go back and forth to this graph. But for now, let's talk about what are the kinds of stuff, what's the information that we're going to try and learn from looking at this graph. And in the big picture, what's going to happen is the information we're going to learn from this graph is the same information we're going to learn from the equation. But I want you to understand it visually first, and then we'll actually go and do some math problems. So the first thing that we oftentimes will be looking at, The domain of the original function. Okay, once again, domain, I like to define domain as all the possible values of x. Or another way to think about it, think of the opposite. Are there any numbers that x cannot be? Now when you're looking at a graph, the domain is very easy. The domain says you look at the graph, and I'm looking at the x-axis. And basically I say, first of all, this graph is continuous. There's no breaks or gaps. So then I say, okay, what's the smallest value of x for this graph? And you notice this graph goes on forever. So if you think to yourself, what's the farthest to the left this graph goes? Well, obviously it's going to be to negative infinity. And then you say, what's the farthest to the right? What's the largest value of x for this graph? And it's going to be infinity. So if you want to write the domain as an interval, you would say negative infinity to infinity. But oftentimes what we'll say, this is the symbol for all real numbers. So basically the domain for this graph is all real numbers. In other words, every value of x, this graph exists, every value of x I could choose along here, I can go and find that the graph exists. This is one thing that's a little different when we go to equations, but I'll explain it how it applies to equations when we get there. So the domain is all real numbers. The next thing we look at are intercepts, and there's two kinds of intercepts, the x-intercept and the y-intercept. Intercepts are where your graph crosses the x or y axis. So it looks to me like if I look at the x-axis or my x-intercepts, the graph crosses the x-axis here and here and here. And by the way, just if you're wondering, I don't know the equation for this graph. I just drew a graph just from scratch just to show you some things. So we're not going to come up with the equation. I'm just trying to show you things. But I see that there are three intercepts, here, here, and here. Matter of fact, if I look here, looks like this is x is -4, x is 0, and x is +4. So I would say x-intercepts, 0, -4, and +4. Now y-intercepts are where the graph would cross the y-axis. And it looks like the value here is y equals 0. So there is an y-intercept of 0. Now if you translate these to points, because in the future when we do equations, I want to graph them, this x-intercept is 0, 0, and -4, 0, and 4, 0, right? Because the x-intercept, the value of y is always 0. Now if I go to my y-intercept, in a sense my y-intercept is going to be 0, 0 again, and I've already got it here. I don't need to repeat it. So actually these are the three intercepts on my graph. All right. Now, the next thing that we would look at are asymptotes. And we're actually going to do a second graph in a minute that will have asymptotes. So let me hold off on this. This graph does not have any asymptotes. So let me hold off on explaining or describing asymptotes, and we'll talk about it in depth on the next graph we're going to do. So there are no asymptotes for this one. Now the next thing we're going to do now, and now we're getting to some of the stuff we've been doing in calculus. Because now we're going to look at the first derivative of our function. The first derivative tells us lots of things. First of all, the first derivative we think of as the slope of the graph. And we think of the slope, we can then determine whether the graph is increasing or decreasing, right? If the slope is positive, we know the graph is going up. If the graph is decreasing, we know it's going down. So initially, if I look at this graph and just decide, okay, where is the graph increasing or decreasing? Well, it starts here. You know, once again, increasing means as you move from left to right, if I'm going up, it's increasing. So it looks like it's increasing. Here I get to this maximum, and then what happens, all of a sudden, it starts decreasing. This is like a negative slope. This is a positive slope, increasing, negative slope, decreasing. It continues to decrease. So this slope is all negative in here, and it bottoms out at this minimum, and then what happens? It starts increasing. So now at this point, my slope would go back and be positive. The key thing I want you to realize is what happened here. I went increasing, decreasing, and then increasing again. Increasing, the slope is positive. When you're increasing, the slope is negative as you're going down, and it's back to positive. Now what happens, what has to happen, if the slope is positive here and negative here, at some point, what had to happen? The slope has to be 0. And where is the slope 0? Right here. Here, we're decreasing, our slope is negative, but when we get over here, all of a sudden our slope is positive. These are called the critical points. Critical points are where the graph changes from increasing to decreasing, or decreasing to increasing. Normally, not every time, but anyways, special things are going on at these critical points. And the key thing to realize is these critical points help us break up this graph into regions. So what I like to do is, at this critical point, we call this region 1, because within region 1, the graph is always increasing, which means the slope is always positive. It's not going to change. Now region 2 is from this critical point to this critical point. So this is region 2. Once again, inside each region, the slope is always going to be, in this case, it's always negative. The curve is always decreasing. But once I get to here, it changes again. So this is going to be region 3. So the regions are where the graph increases or decreases and it doesn't change. Now the key to finding out where these regions are these critical points. And look, these critical points are where the slope is 0. So how does that tie in to the first derivative? To find those critical points where the slope often changes, we take the first derivative and set it equal to 0 and we solve it. So let me try and go over this again just to make sure you understand what's going on. The slope of this graph is the first derivative. Here the slope is a positive number. When it gets to here, at just one point, one value of x, all of a sudden the slope of the tangent line is perfectly horizontal, which means the slope is 0, which means the first derivative is 0. So if I can figure out this value of x where this first derivative is 0, that's going to be my critical point. In this case, it's a maximum. Now if I keep looking at my first derivative, all of a sudden when I get over here, my first derivative is negative. So any value of x I would plug in to my first derivative would give me a negative number. It's negative until I get down to here. And then if I plug in this value of x, it looks like x equals 2. At x equals 2, what happens? My slope becomes 0. And this is our critical point. So what happens is, if I can figure out these two critical points, the values of x for this critical point and for this critical point, then I can now, in a sense, break this graph up into regions where I know inside the regions the first derivative or the slope does not change. And that's what we're going to do mathematically. But I just want you to see here what's going on. Increasing graph, positive slope. At this point, slope is 0, first derivative is 0. You go here, decreasing graph, first derivative is negative, all the way down to the bottom here. At this point, slope is 0, first derivative is 0, and all of a sudden you go up here, and all of a sudden I'm increasing, positive slope, positive first derivative. The key is I want to figure out these two critical points. And the way we do it is, once you take the first derivative, you set it equal to 0. Now from this graph, you can determine where it increases, where it decreases, where it increases. Now, the last thing we're going to do is we're going to look at the second derivative and what kind of information does it tell us. The second derivative tells us about, we'll call it concavity, concave up or concave down. Concave up and concave down, it's almost like in class, it's almost like, is the arc, does this thing open up or open down? There's this thing, it opens up. It's like a U. This one, we say it opens down. So you notice for this graph, this is concave down, right? But you know, over here, all of a sudden it becomes concave up. So what's happened? Somewhere between here and here, it switched from concave up to concave, or concave down to concave up. And what happens is, there's a point in between. This is called the inflection point. The inflection point is when a graph changes from concave up to concave down, or concave down to concave up. In this case, concave down. And you notice in here it's very subtle. It's like where the arc is sort of down, and then we get to here, and then the arc begins to sort of turn into an upward arc. So this is concave up. We would like to know, to figure out this inflection point, and as it turns out, that inflection point is where the second derivative is going to be 0. So that's like our critical point for the second derivative. So just like the first derivative, we set the first derivative equal to 0 and solved it. In this case, to find the critical point of the second derivative, we set the second derivative equal to 0. Now up here, I didn't write it here, but when you solve this equation to find the critical points, those critical points are going to be a maximum, a minimum, or it could be a flat. Here, when you solve this critical point, you're going to find the inflection point. So what's interesting is, and I brought some pins here, if I break up this graph into where the slope changes from increasing to decreasing, so the first derivative, let me do this in red. Does this show up as red? Yep. If I break this up into the regions where the first derivative or the slope changes, then I go from, there's region 1, here is region 2, and there's region 3. So this is the first derivative. This is where the slope changes, or you think of increase, decrease, right? Increase, region 1, it changes to decrease, region 2. Down here it changes back, region 3. Positive derivative in this region, a negative derivative in this region, positive in this region. But let's look at the second derivative, which measures concavity. Turns out this inflection point is where the concavity changes. So for the second derivative, I'll do it in green. The first region is from negative infinity to this point here. Looks like x equals 0. That's the first region, and that is concave down. So concave down this whole region, and then here it flips region 2, and it becomes concave up. So it's interesting how when you look at the first derivative, we're looking at increasing, decreasing, and we break it up into regions based upon where it changes or flips. But second derivative looks up concavity, concave up, concave down, and it's broken up into regions of where the inflection point is. This whole first region is concave down. Here it flips and it becomes concave up. And once again, the key to determine these regions, you have to know these critical points. For the first derivative, critical point is when the first derivative is 0. One critical point, second critical point. For the second derivative, to figure out the regions where the concavity changes, you set the second derivative equal to 0, and you find this critical point, and that breaks it up into regions. Now here's another graph that's different in a lot of ways, very different. Let's just take a look at this and think about some of the information that we get from this graph. This is one that has like 3 pieces, and you see these dashed lines. These dashed lines are asymptotes. So we'll talk about those in a minute. So first of all, if you were to think about the domain, the point is, the domain, there are some breaks and gaps in here, because the domain, we're looking at where does the graph exist for these values of x. Well, I can see for domain, it starts out here at negative infinity, and then it goes, it looks like it goes until x equals negative 1, and then there's a gap. And then once you get past negative 1, the graph picks up again, but then it gets here to, it looks like negative or positive 3, and there's another gap or break, and then it picks up again. So in this case, by looking at this, let me just write it over here maybe, we would say the domain, to make it simple, we'll say R real except when x equals negative 1 and when x equals 3. In other words, negative 1 and 3 are the gaps or the breaks. The domain, the graph exists every place else but those two right there. Now intercepts, I'm not going to really emphasize it here, but there would be looks like a y-intercept here, and a y-intercept here, and an x-intercept here. I'm not even going to put down the values. It's interesting. Not hugely important right now. Now let's talk about asymptotes. So asymptotes are these dashed lines, and normally the graph cannot cross or touch these lines, although what I said in class is true. Sometimes near the center or middle of the graph, sometimes your graph can actually cross an asymptote. And you see that's what happens here. First of all, there are two vertical asymptotes. So you see this graph here, it begins to track the asymptote. It never ever touches the asymptote. And then when you go in the negative direction, it gets very close to this asymptote, and you can see here and here. We also have a horizontal asymptote, and you can see the graph goes like this, never touches or crosses the asymptote, and in the positive x direction here. But what's interesting is this little piece of the graph in the middle, it actually does cross this asymptote. So it can happen where a graph crosses an asymptote, but it almost always happens right there in the center of your graph. Now let's think about first and second derivatives. So let's think about first derivative. Let's think about increasing, decreasing. What is this piece of the graph doing? That looks like it is decreasing. Now here, what am I doing here? It looks like it's also decreasing. And the third part of this graph, as I move from left to right, looks like all three parts of this graph are decreasing. If I were to look at the derivative, the first derivative in these three regions, it'd be negative, negative, negative. Now you notice we do have regions though, because we have breaks here. The breaks in this are caused by these asymptotes, and those asymptotes are where the first derivative is undefined. And that's one of the things we do when we look at functions or equations. We try and see, are there any points where the first derivative is undefined? If it is, we end up having these breaks. So in this case, we would call, let me do it with my red pen again. So first derivative, I'll do it down here. We would call this region 1. We would call this region 2. This would be region 3. These are the critical points that break it up into regions. In this case, the critical points are where the first derivative is undefined. Just to compare, the critical points in our first graph was where the first derivative was 0. So when you have graphs or equations, you have to check two things, two possible critical points, where the first derivative equals 0 or where the first derivative is undefined. And that's why we have to check both. When we do the equations in a minute, we have to check both. There are no maxes or mins. All three of these actually are decreasing intervals. Now, what about concavity? If I look at this first one, this looks like concave down. Then I go here, look at this. This part of it, this is considered concave up. It's sort of a upward arc. Although you notice when I get to here, all of a sudden it's concave down. So what has happened inside of here, we've gone from concavity up here to the concavity is down here, which means inside here, maybe right here, was an inflection point. So actually, these asymptotes also create an inflection point. So for concavity, sort of interesting. For concavity, this is region 1. Region 2 is from the asymptote to my inflection point. Let's look at region 1. Concavity is down. That means second concavity down. Second derivative would be negative. Here, concave up. Second derivative is positive. But from here to here is my third region, and it's concave down. So here the second derivative would be positive. Here, second derivative would be negative. And then finally, region 4, this is concave up, second derivative would be positive. So with this one, turns out there are 3 regions for the first derivative, 3 regions where we look at the slopes, and their critical points are the asymptotes. For the concavity, there are actually 4 regions. We still have the asymptotes, but we actually have a point of inflection here in the middle. And this point of inflection is where the second derivative would equal 0. That's how we would find this point. All right, so that gives you a visualization, maybe graphically, what's going on. Now we're going to actually take a function or an equation and try and figure out all the stuff we just talked about mathematically. We don't have the graph, all we have is the equation. So that first problem, x cubed minus 2x squared minus 5x plus 6. First thing I'm going to do, because it helps a lot of students, f of x and y are always interchangeable. So I'll write it like this. First thing I'm going to figure out, what's my domain? Now when you're looking at equations, the domain always starts out as R real, and then you look for any exceptions to that. And the only time you have exceptions to that, typically when you have equations, is if you have variables in the denominator, like a fraction, which we're going to have in our next problem, or if you have square roots. We don't have either of those here now, so in this case the domain is all real numbers. Intercepts. Sometimes intercepts are easy, sometimes they're not. In this case, the x-intercepts, the only way I can determine the x-intercept is if you set the original equation or function equal to 0 and solve for x. The problem is I don't know how to factor this, and it's very messy. There are probably some x-intercepts, but I don't have an easy way to find them. So intercepts are not essential. So in this case, you just sort of say, I'm not able to determine. It's too much work. It's not worth the effort to try and figure them out. That happens sometimes. Y-intercepts are usually pretty easy because y-intercepts, you set x equal to 0. So if you set all these x is equal to 0, looks like you have a y-intercept of 6, which translates, when you get ready to graph it, we can mark on our graph 0, 6. All right, so intercepts can be helpful. They're not essential, and if they're not easy to figure out, it's okay just to sort of leave them be for now. In this case, asymptotes, normally the only time you have asymptotes is when your original function is like a fraction. When your original equation or function's a fraction, then normally you have asymptotes. In this case, there's no fraction here, therefore no asymptotes for this problem. So now let's go look at the first derivative, and let's review what we're going to try and determine. First derivative basically tells us the regions on the graph where the graph is increasing and decreasing. It will also tell us where we have maybe a maximum or a minimum. Those are the things that the first derivative helps us with. So what you do is we first have to take the first derivative. In this case, it's pretty straightforward. All right, there's the first derivative. Now to find those critical points. Critical points are the values of x where the first derivative changes, oftentimes from positive to negative to positive. Two things we have to check for critical points. The first one is when we set the first derivative equal to 0. So we take our first derivative, say equal to 0, and solve it. Now in this case, the numbers are just not nice and pretty. So you'd have to use the quadratic equation to solve this. And as it turns out, we get two values of x, negative 0.8 and 2.1. Unfortunately, the numbers are not pretty. We also need to check for critical points when the first derivative is undefined. And once again, this normally only happens if you have some kind of a fraction. And since we don't have a fraction here, there's no critical points from this. So based upon this, now is where I go do my little chart. And I go mark these critical points. Once again, these critical points are where the first derivative is 0. And this allows me to break up my graph into regions. And what I'm going to do now is, in each region, I'm going to figure out whether the first derivative is positive or negative, which tells me whether the slope is increasing or decreasing, whether the graph is increasing or decreasing in these regions. So 3 regions. For region 1, let's choose a test point of like -1. Region 2, we'll choose 0. Region 3, we'll choose 3. And here, I'll put, what we're actually looking at is the sign of the first derivative. So I'll write that here, first derivative. So in other words, you put -1 into the equation for the first derivative, and you see what it is. So when I put -1 in here, -1 squared is 1, so I have 3. -4 times -1 is +4. 3 plus 4 minus 5, looks like it equals 2. In region 1, the derivative is positive, which means this is an increasing, the graph is going up in region 1. When I plug in 0, I'm looking at region 2, and I plug in 0 here, ends up equal to -5. Region 2 is a negative region, so inside of region 2, my graph is decreasing or going down. So if it's going up here and down here, you can see that at -0.8, it's like I'm going to have a maximum. What happens in region 3? If I plug in 3, I get like 27 minus 12 minus 5. It looks like region 3 is positive, which means increasing. So once again, I probably have a minimum at 2.1. So at this point, I can actually give, where's my graph where is this equation increasing? From negative infinity to negative 0.8, and from 2.1 to infinity. Where is it decreasing? Well, it's where the first derivative is negative, and it's from negative 0.8 to 2.1. And also, because I know the first derivative changes from positive to negative, at x equal to negative 0.8, looks like we're going to have a maximum. And when x is equal to 2.1, it looks like we have a minimum. Whoops, sorry. So that's all the stuff I was able to learn. Once again, you take the first derivative, you find their critical points. In this case, first derivative equal to 0. You take those critical points, you create your regions. In each region, you determine whether the first derivative is positive or negative. And based upon that, you know your intervals of increase, decrease, and whether you have max or min. That's all the stuff you learn from the first derivative. Now, the last step is to start looking at the second derivative, because it's stuff we can learn from the second derivative. So let me write the first derivative here, so I have it in front of us. Let's take the second derivative. Pretty straightforward. Now, once again, the second derivative tells us about the concavity. Now, to find critical points of the second derivative, we do the same kind of thing. We set equal to 0. We also check to see if there are any points where it's undefined, and there are none, because this only happens when you have some kind of a fraction. So now, based upon this critical point, that's actually an inflection point, and that's where the concavity is probably going to change. So two regions, the little chart again, test point, and in this case I'm seeing what the sign is of the second derivative. I'll put a 0 here and a 1. So if I plug in 0 for x in my second derivative, negative, region 1's a negative region, which means it's going to be concave down, right? Region 2, when I plug in 1 for x into my second derivative, it ends up being a positive number. Region 2 is positive, which means it's concave up. So now, if I look at the intervals, concave up from 2/3 to positive infinity, concave down from negative infinity to 2/3, and then there is an inflection point. At this point, you need to try and sketch the graph, and sometimes it's easy, sometimes it's not. And to be honest, if you're ever having to graph it and you're not sure exactly, you can always just choose values of x and go find the value of y, and you're good to go. I went ahead and looked at these critical points. First of all, let's summarize what were our intercepts. All we determined was 0, 6, because the other intercepts were too hard, so that's 1 point. So that's our y-intercept. We've determined that we have a max and a min. The max was when x was negative 0.8, and I went ahead and before I came here, I worked out the details, and at negative 0.8, the value of y turns out to be 8.2, or actually, this is a minimum. I think I said maximum. Let me look back at my notes. I hope I didn't... Yeah, that's a maximum. And then the other critical point was when x is 2.1, and at 2.1, y was negative 4.1. That ends up being a minimum. Then you have, the last thing we had was an inflection point, and that's when x was 2/3. It's like 0.67. And at the inflection point, the value of y is 2.4. So here's going to be a very rough sketch. Let me plug in all the stuff we've got so far and see what happens. Y-intercept at 0.6. My graph's going to go to that point. I got a maximum at negative 0.8, which is 8.2, so maybe, this is just going to be a rough, maybe right about here. So somehow it's like this. A minimum at 2.1, and it's at negative 4. Maybe like this. And an inflection point at 2/3, which is 0.67 and 2.4. So hopefully you can see it probably looks something like this. One of these kinds of graphs. Now, does this line up with what we found? We found the graph should increase from negative infinity to negative 0.8, which makes sense, and then it decreases from negative 0.8 to 2.1, which makes sense, and then it increases again from 2.1 to infinity. The concavity, concave down from negative infinity to right here, the 2/3, and then concave up from 2/3 to positive infinity. Wow, that was a lot of work, but that's the idea of this kind of problem. Now let me try and do a second one that's different. I'll try and do it fairly quickly. Let me find my notes of the problem so I can do it. This is going to be different because it's going to be a rational expression. So it's going to add some different issues. So here's the function. I can rewrite it like this. Domain, what I said before, domain is normally all real except if you have some kind of a fraction or a square root. I do have a fraction here. What value of x would cause the denominator to equal 0? That's what I have to avoid, negative 1. So the domain is all real except x equal negative 1. So I'm going to have a gap or a break when x is -1. Intercepts, let's see, how about x-intercepts? So if I set y equal to 0 and try and solve for x, you can see if I multiply both sides by x plus 1, I end up with this. So as it turns out, I do have an x-intercept to 0. So when I get ready to graph it, how about y-intercepts? So you set all the x's equal to 0. Looks like I have a y-intercept of -2, which translates to the point 0, -2. Now, since I have a fraction, I will have asymptotes. Vertical asymptotes, you look at the values of x that cause the denominator to be 0. It's the same idea we were looking at the domain. So if I have, this is my equation, what value of x would cause the denominator to be 0? That's going to be my vertical asymptote. When we do the graph, I'm going to go to x equals -1 and draw a vertical dashed line up and down. Now you remember in class I talked about horizontal asymptotes. You just compare the leading terms. The leading terms are the variable term with the largest exponent. So you eliminate these right here. End up with x over x. The x's cancel out, end up with 1. And that's what happens. When the leading terms have the same exponent, it's just the ratio of the coefficients. So I'm going to have a horizontal asymptote of y equals 1. So when I draw my graph, I'm going to go at y equals 1 and draw a horizontal dashed line for horizontal asymptote. Now let's see what happens with first derivative. First derivative tells us we go find critical points, and then it tells us whether the graph is increasing or decreasing in the regions. So let me write down the original function. First derivative, I have to use a quotient rule, right? Whatever's in the bottom, derivative of the top is just 1 minus the top times derivative of the bottom, which is 1 over the bottom squared. Now if I try and simplify this, this is going to be x plus 1 minus x minus 2. So x minus x, the x's cancel out. You have 1 minus a -2, which is 1 plus 2. You end up with 3 in the numerator. And your x plus 1 squared. And let me get a new page. Let me rewrite this first derivative. Because now we have to go find our critical points to break up our graph into regions of increasing or decreasing. So once again, here was the first derivative. First thing I do is I set it equal to 0. But if you look closely, if I try and solve for x, there's no solution. There's no value of x that's going to cause that first derivative equals 0. So there's really none. However, now if I check, there are any values of x that make this undefined, and there actually is, because -1 would cause the denominator to be 0, and then it would be undefined. So this is my critical point. It's not going to be a max or a min, but it is going to break up my first derivative into regions, in this case 2 regions. Test point for region 1, I'll say -2. For region 2, I'll say 0. Now we're going to see what happens to the first derivative in these regions. So now if you look at the first derivative and you plug in -2, you notice the denominator, because we're squaring it, it's always going to be positive. And you plug in 0, it's still positive. So it turns out both these regions are positive. So there's going to be some kind of break or a gap. But the graphs are both increasing in both regions. Sort of interesting. So if I say intervals of increasing, -infinity to -1, and -1 to infinity. And there's no region of decrease. So the graph is always going up. And there's no maxes or mins. So let's go on to the second derivative. So, just for fun, let's actually rewrite the first derivative. Let's take the second derivative based upon this. So -6 x plus 1 to the -3. Chain rule says derivative what's inside is just 1. I could use the quotient rule, but I decided to just do something different. So here's my second derivative. Now, once again, I want to find the critical points. So I say, well, what are the values of x that cause the second derivative to equal 0? But as it turns out, there aren't any again. So that means there's not going to be any points of inflection. However, let's check out critical points where the second derivative is undefined, which means, is there a value of x that causes the denominator to be 0? And once again, there is at -1. So we have two regions. -1 breaks it up. Test point will go -2 and 0. And in this case, we're seeing what the sign is, the second derivative. So you plug in -2 into here. You notice the denominator is negative, because -2 plus 1 is -1. -1 cubed is -1. -6 over -1. The second region 1 is a positive, which means it's going to be concave up. Region 2, when I plug in 0 into my second derivative, the denominator is positive. I got the negative up here. Region 2 is negative, which means region 2 is concave down. And no point of inflection. So basically, that's all the information we have. So let's sort of summarize what we have and see if we can figure out what in the world the graph might look like. So we had some intercepts, 2, 0, and 0, -2. We had some asymptotes, x equals -1 and y equals 1. Now we had regions of increase only, 2 regions. And we have concave up and concave down. So based upon that information, are we somehow able to figure out what a graph might look like? And once again, if you're not sure about it exactly, you can always just plug in some points. Intercept 2, 0, 0, -2, asymptote x equals -1. So this is where the graph cannot cross or touch this asymptote. We also have an asymptote of y equals 1.